Colleagues, I welcome you back to this online tutorial on structure and bonding designed for students in Senior 5 and Senior 6, offering chemistry as a part of their subject combinations. So here we are to explore the factors that influence a covalent bond, strength of a covalent bond, factors that influence strength of a covalent bond. Before you explain these factors, we looked at factors that influence strength of a metallic bond, factors that influence strength of an ionic bond. Now, these are the factors that influence strength of a covalent bond. First of all, what is a covalent bond? In class, I defined what a covalent bond is. Covalent bond, recall that from what you have there in your notes, a covalent bond is a type of bond formed when electrons are shared. For example, a bond between carbon and hydrogen, where carbon contributes and hydrogen contributes. So it is a type of chemical bond which is formed when electrons are shared in pairs between bonding atoms. Like here we share carbon and hydrogen share one pair of electron. One pair, how does it come about? Carbon brings one electron, hydrogen also brings one electron, so that we have one pair of electrons. So this is a covalent bond. We are looking at, first of all, before you just jump into anything, you have to understand which type of bond are you dealing with. This is a bond between atoms. It is a bond between atoms. So what is the first factor? The first factor is the size of an atom. The size of an atom. I want to say that for the size of an atom, we look at the case where the atom is big, where these atoms are very big, where these atoms are very big. And also when they are small, an example of a very big atom, you can think about which example can I give? These examples are difficult to think about. A very big atom, for example, you can look at iodine. Iodine is big. Now you may ask me, teacher, why have you chosen iodine? Okay, maybe I leave these examples because some of you haven't covered atomic size. That's why I have not even called it atomic radius. In some books, they call it atomic radius. Atomic radius is the same as size. Yeah. Now, okay, I think I should do, because some of you haven't covered the atomic size. Let me not use examples. Let me leave the examples alone. So we are looking at the size of an atom. Now, we can have atoms that are big and atoms that are small. Now, if you have big atoms and atoms that are small, think about this carefully. These big atoms, they are big, they are fat. They walk slowly by slowly, so that they link up. They walk slowly by slowly, so that they link up. However, if you have atoms that are small, they walk quickly so that they link up. Therefore, since these ones that are big, closely approach each other, or they kind of take a very long period of time to share electrons, so they form a longer bond. Why? Because they take some time to closely approach each other. So this bond is long. However, this bond is short. Some time back, I gave you an example. I don't know whether you recall that example. Think about a jerry can, a 20-liter jerry can. Cut that 20-liter jerry can into pieces. Do you know what you are doing if you cut the 20-liter jerry can into pieces? Okay, I think will that example work? Okay, let me leave it. Okay, you have these big atoms and also these small atoms. The ones that are big, they are fat. Fatties. They do not closely approach each other at a faster rate as compared to these that are strong. So for atomic sizes, you see that This bond now is long, it is long, therefore if it is long, it is weak. If a bond is long, is very weak. Why? One can easily break it if he or she supplies heat energy here. A bond that is long is weak. Sometime back, I gave you an example of a jelly can. Cut a jelly can into pieces. Do you know what you are trying to do? You are trying to elongate that jelly can. If you cut a 20-liter jelly can into pieces, you are elongating it. So you are making it weak. Now, if you put that jelly can which you have cut into pieces, if you put those pieces of the jelly can into fire, you have those pieces of the 20-liter jelly can into fire, then you also have another 20-liter jelly can which is not cut into pieces. For example, this one here, which is not partitioned. Now, these ones which you have cut them into, which you have cut into pieces, these pieces, for them they are elongated. It's like you have tried to loosen this jelly can, to lose. You are trying to expose it by cutting. Therefore, if you compare this one which is compact and this one which is exposed, if you put them in fires that are burning at the same rate, these pieces will burn at a higher rate. Why? These pieces are weak. They are not compact as compared to this one which is compact. Do you know how this one which is compact will boil? It will first coil itself. Have you ever put a plastic bottle into fire? It first coils itself because of that strength. So I want to say that if you have the strength of a covalent bond is inversely proportional to atomic sizes. The strength will be high. The strength will be high if the sizes are small. The strength, I'll repeat, the strength will be high if the sizes are small, and the strength will be low if the sizes are big. Larger atomic sizes, the larger the atomic sizes of bonding atoms, the longer the bond length and the weaker the bond strength. The smaller the atomic sizes of bonding atoms, the shorter the bond length and the greater the bond strength. Colleagues, as of now, I am running out of time. Allow me stop this here. The first factor has been explored. Strength is inversely proportional to